This is topic 9.1, Introduction to Entropy. Hashtag not sponsored by Nintendo or the Super Mario Brothers movie or anything like that. Okay, so today's objective, identify the sign and relative magnitude of the entropy change associated with chemical or physical processes. So we need to look at how energy and matter kind of are related to entropy in this particular topic, some essential knowledges we need to know. So we may look at kinetic molecular theory, solid, liquid, gas, all that type of stuff. So we were supposed to be introduced to entropy in Unit 7, but I postponed it until Unit 9. So entropy, symbolized by S, can be described in different ways. Entropy is a measure of the thermal energy of a system divided by a unit of temperature, usually in Kelvin. This energy is unavailable to do useful work. It can also be thought of as a measure of the energy lost to molecular disorder or randomness in a sample. The unit for entropy is joules per Kelvin. Positive values indicate that the system increased in entropy, while negative values tell you that the entropy decreased. So positive value means you're increasing entropy. If you get a negative value for entropy, that means it decreased in the system. The third law of thermodynamics, you should know that from probably biology, chemistry, whatever. Yeah, somewhere. You probably should have learned this by now. The third law of thermodynamics is that entropy of a perfect crystal at 0 Kelvin is considered 0. So let's look at these two particles in a very tiny container. Imagine that the container has two sections. There is one way to have both particles on the left, there is one to have both on the right, and there are two ways where you can have one particle on each side. It is more probable to have one particle on each side, which means that if we have a system with two particles in two sections, most likely at any given time we're going to have particles that are going to be spread out. In an actual system though, like a beaker or balloon, you can have a huge number of possible sections. We call these microstates. When the particles or energy in a system are more spread out into the microstates, we can say that there is more disorder or entropy. The closer they are, the less spread out they are, we can say that there is less entropy or disorder. Consider the common phases of matter: solid, liquid, and gas. Solid, you have a regular arrangement, while in liquids, they're not as regular, they're able to move. Particles are not spread out in a solid versus in a liquid where they're constantly in motion and can move throughout the system. They are in more microstates, so they have a fixed volume and have a greater entropy than a solid. Solids have the least amount of entropy. Gases have the greatest amount of freedom of molecular motions and fill the volume of their container, stuff that we already know. So this increases disorder, therefore there is more entropy, greater number of microstates. Gases have a lot more entropy than a liquid or a solid. So if you place the same amount of gas in two different containers with two different volumes, and it's the same temperature, the gas in the one container will have a greater volume and a greater entropy because there's greater disorder and there's more dispersal of the matter in a larger container. So we're going to see the equation for entropy in a bit, and just something to be mindful of when we see this at some point, that if there's an increase or decrease of entropy, you can look at that by comparing the moles of gas on each side. If the products have more moles of gas, we can say that the entropy is increased. Delta S is positive. Entropy also increases when energy is more dispersed within a system. So that means that we can look at terms of temperature. Based on the kinetic molecular theory, if the system will have higher temperature, it will have greater average kinetic energy, greater dispersal, greater energy distributed, therefore greater entropy as the temperature increases. So stuff you kind of know already. Entropy increases, systems become more disorganized. Decomposition reactions are an example. Increase in temperature is related to that. Dissociation of ions from a solid into aqueous. Endothermic changes, solid, liquid, gas. Increasing the number of moles. Gas expansion, so increasing the volume, decreasing the pressure. So both examples shown here in this diagram with the decomposition reaction, and you have a solute and added to a solvent and make a solution. Entropy is increasing, more disorder, more disorganized, more moles, etc. So the opposite is for entropy decreasing, less disorganized. Composition synthesis reactions are an example. You're decreasing temperature instead. You're precipitating or forming a solid, so the reverse. Exothermic phase changes, gas, liquid, solid. Decreasing the number of moles, gas compression, increasing pressure, decreasing volume. For each of the following pairs, choose a substance with the higher entropy at a given temperature. Explain your reasoning. So we have carbon dioxide gas and carbon dioxide solid. Helium at 2.0 atmospheres and helium at 0.020 atmospheres, and calcium carbonate and calcium oxide and CO2 gas. So for the first one, so we have calcium, sorry, I keep on saying calcium for some reason, I don't know, carbon dioxide gas and solid. So of the two, which is going to have the higher entropy? Most likely for the first one, it's going to be carbon dioxide gas. Since it's in a gaseous state, there's particles in more random arrangement in comparison to the solid phase. Next, we have helium at 2.0 atmospheres and 0.020, they're both gas. So of the two, who's going to have the high entropy? Most likely it's the one with the lower amount of pressure, which means it has greater volume. With a greater volume, there's going to be, with a greater volume, there is going to be greater volume, there is going to be more space, if you will, more expansion for the particles, random particle arrangement, and therefore there is more chance for disorder, entropy, chaos, however you want to look at it, in comparison to you have a situation where it is more compressed. Calcium carbonate and then calcium oxide and CO2. Of the two, which is more entropy, the one that's going to have more gas, if you will, has more entropy than something that is just a solid. So, last one. The formation of ammonia is an exothermic reaction that is spontaneous at low temperatures, meaning it just happens on its own. So we have nitrogen gas plus 3 hydrogen H2 molecules forming 2 ammonia molecules. Complete the reaction showing one of the nitrogen molecules reacting with the hydrogen. Okay. Okay, very good. All right. So on the left side, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 gas molecules. So we have one of our nitrogen molecules reacting with hydrogen. So it looks like this is my nitrogen molecules here. And then so I'm going to form ammonia on the other side. So for 1 and 2, it's going to break up. So let's say, so this is going to break up. Well, I'm probably going to use the same color. So we're going to break that one up into here and here. That means now that for each of these, we need how many of my hydrogen molecules kind of used up, so to speak. So I'm going to take this. So now that is going to be only 2, so I need another one here. I'm going to use that remaining H over here. Then I need another one. I'm going to use that here and here. So from that 1 and 2, I'm going to make from the 1 and 2 and the 3 H2s, I'm going to make make 2 ammonia molecules. So then now I still have the leftovers. So let's say I use this one up. Looks kind of like Squidward sleeping. Hashtag not sponsored by Nickelodeon either. So I also have 1, 2, 3, 4. Those are still connected, sorry. Then that and then that. Okay, so did the system of the entropy increase or decrease in the system? Well, what happens? So we had 10 initially. Now we have 1, 2, 3, 4, 5, 6, 7, 8. Now we have 8 gas molecules on after the reaction occurs. Entropy decreases since we have fewer. There are fewer gas molecules. Okay, so if you have any questions, please let me know. Thanks.